Welcome back, everybody. It's my pleasure to introduce the next speaker, Tamas Budavari, Associate Research Professor of the Department of Physics and Astronomy at Johns Hopkins University. His work spans cosmology, large-scale structure, galaxy evolution. That's all the work. I've just met him for the first time right now in person, but I've seen his work over the years a lot. And as we saw from Alex's talk, a lot of his focus has been on the statistical and computational challenges in astronomy with these large data sets. This afternoon, he's going to be giving us a nice lecture on multiple object detections in time domain surveys.
Thank you very much. Thank you very much for the organizers having me here. It's great to be here. Nice lecture, I don't know about that. This is a work in progress. This is a project that we are currently actively thinking about. Alex and I have been confronted with a couple of challenges recently. These are actual problems that we face with catalogs. And so these are just thoughts arranged around the topic. Okay, for those of you who are not astronomers, I have to start with this slide. Astronomy is beautiful. I always thought that we have to combine data so that we can look at the objects out there in different wavelengths and use all that multicolor information to learn more about the universe. But today it's only there because it's beautiful. The real reason, of course, for combined data is today time domain astronomy. Okay. Lots of things happen in the sky, they go bang and then disappear, or just do ups and downs. And what we have is just a snapshot of that. Lots of sequences of images. And we have to make the best of that data somehow. All right, so time series. How do you do that? How do you get a time series in the first place? So maybe it's a very basic question, but ideally, it's just wait for all the images to be in your database or on disk, and then you co-add them. When you add them together, you figure out where all the sources are, and then you can go back to every one of the images and measure the fluxes, the function of time. Okay. So that would be perfect, except you would have to wait for a long, long time to have all the images that you have. And it would be so much nicer to have something that's incremental, that's streaming, something that can go from image to image without the need to store and go back to previous images. And if you want to do that, you have to dig in the noise, and that makes things a little messy. And that's my goal. See if we can find some sort of incremental strategy to weed out noise or find the real sources, and if possible, do it from first principles. Again, work in progress. All right, so the outline is for today. Cross-matching catalogs, very briefly. I know several of you have heard me talking about cross-matching at length. Now I'll just sort of briefly summarize some of the key ingredients of the probabilistic cross-matching, because these are ingredients that can actually come handy, very useful for looking at the problem that I want to address today. And then I look at what's the probability of detecting something in single and multiple exposures. And then the third question, this is on to you. The question, are given observations, do these observations correspond to real sources or not? Okay. Typically, it's a good idea to separate out several challenges. We face statistical, computational, and astronomy challenges every time we do something. What I'll talk about today mostly is going to be statistics. However, I'll point out some of the elements that we have or in place or use to make these computations feasible and fast. But those I consider sort of separate problems, one at a time. First you solve the statistics problem, then you solve the computational problem, and then you have science left, hopefully. All right. So first thing is cross-matching. the key to this problem turned out to be finding the right question. The right question is not how far things are on the sky, and so on and so on. The good question is, are the detections the same or not? So if you are given a bunch of measurements, and here I have a data set that consists of just direction on the sky. Okay? These are locations of directions that you have in hand. You can ask the question, are these measurements consistent with being the same object or not? And that you can ask in a Bayesian framework using hypothesis testing. The quantity that plays an important role here is the Bayes factor, which is actually the likelihood ratio. It's a likelihood of the hypothesis that says, yes, they are the same, versus the other one that is the complementer, which says, no, any one of them could be coming from a different source. Okay, so how do I compute this? One of these things is simply just parameterize that hypothesis and integrate over the entire parameter space. So the first one says they're all from the same object. If it's the same object, it has to have one true location on the sky. That's my parameter M. Okay. Then I can write up the integral that says this true position could be anywhere on the sky. That's my prior. And then the likelihood that says, given the true position, what are the possible observations? And just put independent measurements. Okay, so simple integral. And then, similar to the complementer, you actually have a set of locations, because any one of them could be coming from the different source, so a set of NI locations for the truth. And then the integral falls apart in a different way. In fact, this is even easier to compute than the other one. Now, this is not as bad as it looks. If you plug in a normal distribution or a Fisher distribution, then actually it's a nice analytic formula. So all you have to do is work through the math, and it's Gaussian, essentially, spherical Gaussian, Fisher distribution, spherical normal distribution. So it's all simple and analytic. Okay. Now that's not the end of the story. You want to get the probability, and how do you get that? For hypotheses that are complementary to each other, there's a simple rule that says, from the prior I can use the posterior just using the Bayes factor, because it's a direct consequence of Bayes rule that you can apply to both hypotheses and then solve the equation for the posterior probability. This is essentially 1 minus PH is the complementer. But anyway, the problem is that we don't have a prior. And it turns out that it's not so much important because large posteriors are fairly insensitive to small variations, so you can have an educated guess that works. Or you can use some empirical Bayes techniques and actually solve for it. So that's the trick, that's the key to it. So with that, we can actually do cross-matching, and we know what the statistics are. Okay. The computational component is, well, let's do it on GPUs. Those are fast. You can run 25,000 threads on a single card. Let's use it. We have a new implementation that we just released on GitHub, which is using a portable implementation in C++. The Boost library provides threading so that the CPUs can drive the GPUs, and you can use as many GPUs you have in your system. We have tested this up to 7 GPUs. That means 7 times 25,000 threads running in parallel. It's a lot of threads. And with that, we can cross-match Sloan to itself in 3 minutes. Okay. So these are kind of stepping stones that we are building on to get up to the challenge that LSST and the new surveys present, because we have to do this kind of cross-matching all the time as data come in to find matching things and building up the time series. Okay. There's a shameless plug for a project that we completed recently with Steve Lubo at Space Telescope. Here we took the entire Hubble Legacy archive and cross-matched all the observations. The data itself is not humongous, it's about 1 terabyte. But some part of the sky covered hundreds of times or thousands. That by itself represents quite a bit of computational challenge. And on top of that, the astrometry, the accuracy of the positioning of the field is all over the place. So if you were to do some cross-matching with that photometry, you would get this curve down here. Okay, so peak is at 20 milliards seconds. Huge. We have a very efficient and nice solver that runs inside a database that can correct for the astrometry of each image that's involved in a cross-match, groups of images overlapping, and that will give you a new peak, a new histogram of hairs that you will find these. It is just essentially the absolute optimal that you could get, relative accuracy of the image. So sometimes just a few milliards seconds. Okay. So with that, we have reliable. Now on the right-hand side, you see is time series, is how many matches we have with a given time span. Okay, so say you wanted to do time series science with Hubble data, you would have up to let's say 300 or 200 days. You would have 600,000 matches to play with. If you want to go out to 1,000 days, there's still 200,000 matches. A lot of data there that could be exploited. And this is something that's going to be released real soon at the AAS. Okay, so that's the shameless plug. Now, okay, so what's real? As I said, it's a real problem in a sense that some of the catalogs that we see today are overwhelmed by junk. And we had seen it before, didn't know what to do with it. Now we have time series, so there's a chance to read these things out better than before. And why it's important? Because there's money involved. If more than half of the data is junk, then you have to have twice as big databases built for them. And so the idea is to find an online method to prune these things as the data is collected, as the survey goes on. Okay, so let's start with something simple. Imagine you have a real object with a given flux. We know how bright it is. Its true apparent flux is F. We measure it with an uncertainty. So epsilon is, and it comes from a Gaussian, and it has a sigma variation. That's a reasonably good model for astrometric measurements in flux. So we have some Fi, which is the noisy measurement. We can ask the question, what's the probability of a given object with a true flux F being observed? When your catalog is cut, there is a threshold that's applied. The threshold, if that's Fd, essentially is the only parameter that enters the equation. You have the Gaussian, you need to have a tail, you get the error function. It's that simple. And what you get is curves like this. So you take 2, 3, 4, 5 sigma, and you get these green dotted lines. The sigma is going up. Well, the error function, that is. Right? Now the red lines here are when you actually have a stack. Say you have 9 images that you merge together. Essentially what happens is the error shrinks, and then everything gets a bit sharper. Okay. Now if you have multiple exposures, then you can ask the question, what's the probability for a given flux F that I will see this source n times out of k exposures, like k observations. And this is what's shown with the red curves here. These nice curves going up and down is the 1, 2, 3, 4, 5, and so on to 9 observations. It's just a third of the function of the flux. The flux is, as you can see it, goes from 0 to 7 in sigma units. That's the blue curve here is the cumulant. When you add up, so it's n or more. Okay? So this is the probability that you see it once or more, 2 times or more, and so on. And what you can see here is that these curves actually go quite similar to what you would get with the stacks. And in fact, if you overput them on top of each other, if you remember, the yellow curve was essentially a 9-way stack and detection of that. And then the blue is essentially just doing a catalog-based coed in a way. The probability of seeing something is very similar, especially if you look at this second one. This is the 3 sigma curve, the 3 sigma threshold, very similar to the 5 detection out of 9. So these are not that different, in fact, very similar. So there's hope where you can, from here, could conclude that, all right, that you could conclude that you could do the same thing with a catalog, or very similar that you can do with the image. So how do we do it backwards? So in real life, we actually have observations and non-detections. How do we combine this together? Well, if you just have a single exposure, then you have a single detection, say Fi, and then you can do the same type of hypothesis testing we did before and compare real versus noise, where the real says, oh, I have a pi over the apparent flux, and then I have the likelihood for one detection of the Gaussian. So integral, the noise is easier because there's zero flux there. Okay. Now, what's the prior on the apparent flux? Well, that's something actually astronomers measure. So we measure the so-called number counts. For example, galaxy number counts go as 1 over s squared. The problem with that, 1 over s squared goes to infinity if f equals 0. So luckily there is a solution to this, which is there is a threshold. For stars, you run out of stars. You have to hit the edge of the disk. For galaxies, it's essentially the oldest paradox, the dark max height paradox. And there, the combination with going back in time as you farther and farther away, you have the population of galaxies, and eventually you hit a limit, which can be estimated from really deep observations. Okay, so with that you can write the inverse problem, and you just have to make up the likelihood function for your multiple detection. And if you have a component that has a binomial distribution, and it has the component that is the fluxes. Okay. Right. So noise is different, and I didn't think it would be that complicated. The noise is a continuous Gaussian random field, and over that, when you look for local maxima, you can actually generate a point process, and things get complicated. But luckily, this is something that can be computed. In fact, it has been done. One of us has done it. This, 30 years ago, there was a famous BBKS paper, which essentially did the same type of calculations in 3D, which is harder. So there's hope that one can do this. It hasn't been done, we haven't done it yet. However, we have done some hand-wavy arguments about geometry and sizes, how big the PSF is, the blur and so on, that mixes the different pixels. And this is just sort of first results, looking at LSST image simulations. So this is actually a simulation of an image simulation. So it's not real data, but what you have here is essentially realistic things, and here in the corner are still the noise values. On the right-hand side, you have the functional magnitude of flux. The real source is 1,000 sources here, and the noise 1,000 sources there on the objects. And as you can see, there is a really nice intuitive result. The number of times, discreteness, number of times you see it is very important, and then the fuzz, the blur, is introduced by the flux measurement. Now, this is, of course, different every time. You have different thresholds, so it can shrink if the threshold is different. Also, the blur can be different. So this is something that is currently being studied, and we don't have conclusions yet. So with this, we can hope that during a survey, you can maintain real objects, junk objects, and somewhere to keep track of them for future reference, and you can prune as you go. So that's what I wanted to say. Now, with that, you can hope to have a streaming implementation and build a pipeline that will essentially work with independent catalogs of the images and combine them optimally. And this could be, in general, extended to have models that very variable stars So there's lots of things to be done, but is that just sort of the first steps, and that's where I stop. Thank you.
Questions here?
I was about to ask you about the last challenge, the extension to variable sources. What if you have an intermittent source that only occasionally peaks sub-significantly, but enough times that altogether, in principle, you can lower the source, if you know which observations work?
That's a very good question. I mean, I would hope that, if it does it all the time, it's truly periodic and it will come back. No, it just happens once, a few times.
But you don't know it.
Let's think about it. The coffee break. Over coffee.
You mentioned about having a stack of images where you can then predict how many times something will be seen. But suppose you knew the possible nature of an object likely to be lurking there, then how do those models change, and is something of that kind going into your thinking?
If you
If I tell you that at this pixel I expect this particular kind of object, say a CV, which I know should vary in such and such fashion, then does the computation change?
Right. So if you have time information, if you have the epochs, which you do, then you can of course essentially vary your ground truth as you do the integrals in that kind of flux. So your apparent flux will be time dependent, but you will just have essentially a parameter that.
Any other questions? Okay, let's thank our speaker again. Welcome back, everybody. It's my pleasure to introduce the next speaker, Tamas Budavari, Associate Research Professor of the Department of Physics and Astronomy at Johns Hopkins University. His work spans cosmology, large-scale structure, galaxy evolution. That's all the work. I've just met him for the first time right now in person, but I've seen his work over the years a lot. And as we saw from Alex's talk, a lot of his focus has been on the statistical and computational challenges in astronomy with these large data sets. This afternoon, he's...
I always thought that we have to combine data so that we can look at the objects out there in different wavelengths and use all that multicolor information to learn more about the universe. But today it's only there because it's beautiful. The real reason, of course, for combined data is today time-domain astronomy. Okay. Lots of things happen in the sky, they go bang and then disappear, or just do ups and downs. And what we have is just a snapshot of that. Lots of sequences of images. And we have to make the best of that data somehow. All right, so time series. How do you do that? How do you get a time series in the first place? So maybe it's a very basic question, but ideally, it's just wait for all the images to be in your database or on disk, and then you co-add them. You add them together, you figure out where all the sources are, and then you can go back to every one of the images and measure the fluxes, the function of time. So that would be perfect, except you would have to wait for a long, long time to have all the images that you have. And it would be so much nicer to have something that's incremental, that's streaming, something that can go from image to image without the need to store and go back to previous images. Okay. If you want to do that, you have to dig in the noise, and that makes things a little messy. And that's my goal. See if we can find some sort of incremental strategy to weed out noise or find the real sources. And it's fun.
going to be giving us a nice lecture on multiple object detections in time-domain surveys.
Thank you very much. Thank you very much for the organizers having me here. Great to be here. Night spectra, I don't know about that. This is a work in progress. This is a project that we are currently actively thinking about. Alex and I have been confronted with a couple of challenges recently. These are actual problems that we face with catalogs. And so these are just thoughts arranged around the topic. Okay. For those of you who are not astronomers, I have to start with this slide. Astronomy is beautiful.